February 15, 1943, Sidi Bouzid, Tunisia. The German attack came at dawn. Panzers of the 21st Panzer Division, supported by elements of the 10th Panzer Division, struck American positions in a coordinated assault that demonstrated everything the Afrika Korps had learned fighting the British for 2 years. The U.S. forces, primarily from the 1st Armored Division, were green. 5 days in combat, no experience with German tactics, poor positions, inadequate reconnaissance. They were about to receive a brutal education. Within hours, American positions collapsed. German armor overran defensive positions, destroyed dozens of American tanks, and captured hundreds of prisoners. It was one of the worst American defeats of the North African campaign. Among the captured American equipment was an M4 Sherman tank, not destroyed, captured intact with only minor damage. The crew had bailed out, but the tank was operational and serial number and unit markings identified it. War Daddy 2, belonging to the 1st Armored Division. German field commanders immediately recognized its value. They'd been fighting Shermans for weeks and knew the type well, but this one was intact enough to study in detail. Orders went up the chain: ship this tank to Germany for comprehensive technical analysis. March 1943, Kummersdorf Proving Ground, Germany. War Daddy 2 arrived at Germany's premier weapons testing and evaluation facility. This was where German engineers tested captured Allied weapons to understand their capabilities and weaknesses. It was where the Panther tank had been developed partly in response to encountering Soviet T-34s. The team assigned to analyze the Sherman expected routine work, document the inferior American engineering, confirm German technical superiority, write a report validating that German tanks were better. They were professional engineers. They began with measurements, photographs, and systematic disassembly. What they found challenged everything they'd assumed about American manufacturing, tank design, and the nature of industrial warfare. Their report, preserved in German military archives, later captured by Allied forces and now available to historians, reads very differently from what they expected to write. This is the story of what German engineers discovered when they tore apart War Daddy 2. How captured German documents revealed that Nazi engineers were simultaneously impressed and horrified by what American industry had built. Why the Sherman's inferior design features turned out to be brilliant industrial engineering. And how a tank everyone knew was worse than German tanks on paper proved to be designed for something German tanks couldn't match: mass production, field maintenance, and sustained industrial warfare. The context: what Germans expected to find. To understand why the Kummersdorf findings mattered, you need to understand what German engineers expected. German tank philosophy in 1943. German armor design emphasized superior specifications, thicker armor, more powerful guns, better optics, engineering excellence, sophisticated mechanical systems, precision manufacturing. Battlefield dominance: German tanks should win tank-versus-tank engagements through superior performance. Craftsmanship: quality construction, careful assembly, skilled labor. The Sherman's reputation. By early 1943, German tankers and commanders knew the Sherman from combat in North Africa. Inferior armor: 50 mm frontal armor, sloped, versus 80 to 100 mm on German heavy tanks. Inferior gun: 75 mm M3 gun with mediocre penetration versus long 75 mm or 88 mm German guns. Inferior profile. Tall silhouette presenting larger target. Inferior performance. German tanks could engage and destroy Shermans at ranges where Shermans couldn't effectively fight back. The expected confirmation. German engineers anticipated the Kummersdorf analysis would confirm American manufacturing was crude compared to German precision. American design was unsophisticated. Sherman components were of lower quality than German equivalents. The tank was inferior in every measurable dimension. German engineering philosophy was validated. They were partially correct and completely missed the point. The first shock, interchangeable parts at unprecedented precision. The first major discovery came when engineers began disassembling major components. The test? Engineers removed the transmission from War Daddy 2. Standard procedure when analyzing any vehicle, examine the transmission for design, materials and manufacturing quality. Then someone suggested a test. They had spare Sherman parts captured from other destroyed tanks. What if they tried installing a transmission from a different Sherman, one built at a different factory? The result? The transmission from the other Sherman, built at a different manufacturer, months apart from War Daddy 2, fit perfectly. Not approximately. Perfectly. No hand fitting required. No modifications needed. Installation took hours, not days. From the Kummersdorf report, the interchangeability of components is remarkable and represents manufacturing capability we have not achieved. We removed the transmission and installed a transmission from a different vehicle manufactured at a different facility. The fit was perfect. No modifications were required. Installation was accomplished in 4 hours. This suggests American manufacturing tolerances are far more precise than we estimated. The ability to produce truly interchangeable components across multiple factories simultaneously represents industrial capability of the highest order. Why this shocked German engineers? German tank production used precision manufacturing, but each factory had slight variations. Components manufactured at one plant often required hand fitting to be installed in tanks from another plant. This was accepted as normal. Even components from the same factory sometimes required adjustment during assembly. Skilled craftsmen would file, adjust, and fit components to achieve proper assembly. The Sherman's complete interchangeability across multiple manufacturers was unprecedented in German experience. The industrial implication. True interchangeability required. Extremely precise manufacturing tolerances across all suppliers, rigorous quality control at every factory, standardized specifications enforced industry-wide, manufacturing technology capable of consistent precision at scale. This implied American industrial capability far exceeding German estimates. The second shock, designed for field maintenance. As engineers continued disassembly, they discovered the Sherman was designed with field maintenance as a primary consideration. The accessibility principle. Every major component on the Sherman was accessible for removal and replacement by field mechanics with basic tools. Engine access. The radial engine could be removed and replaced in hours. Access panels were large, well-positioned, and held by standard fasteners. Transmission access. The transmission was accessible from both inside and outside the tank. Removal didn't require disassembling the entire vehicle. Track maintenance. Tracks used rubber blocks bolted to steel links. Damaged sections could be replaced in the field without specialized equipment. Weapons maintenance. The main gun could be removed and replaced at battalion-level maintenance, not just at depot facilities. From the Kummersdorf report, the vehicle is designed for rapid field maintenance. Major components can be accessed and replaced with basic tools and equipment, available at battalion or regimental level. By comparison, our own vehicles often require specialized tools, factory-level facilities, or extensive disassembly to access major components. The American design philosophy appears to prioritize maintainability and rapid repair over maximum performance. This is a different approach than our own, and its implications for sustained operations are significant. Why this mattered. German tanks often required specialized mechanics with extensive training, factory-level repair facilities for major components, specialized tools and equipment, extended time out of service. The Sherman could be maintained by adequately trained battalion mechanics, repaired with standard tools which returned to service quickly, maintained in field conditions is the operational impact. A damaged Sherman that could be repaired in 24 hours at battalion level versus a damaged Panzer that required 2 weeks at a depot facility meant the Sherman was operationally available more often. The third shock simplified crew operations. German engineers noticed the Sherman's controls and crew stations were designed for simplicity and ease of use. Driver controls. The Sherman used a synchromesh transmission similar to a civilian automobile. Shifting gears required moderate skill, but was far easier than the complex transmissions on German tanks. From the Kummersdorf report. The transmission is synchromesh type, similar to civilian automotive practice. This simplifies driver training and reduces fatigue during extended operations. Our transmissions require greater skill to operate efficiently. This provides some performance advantages, but increases training time and crew fatigue. Turret controls. The Sherman had power traverse for the turret, electric or hydraulic systems that rotated the turret with minimal physical effort from the gunner. Many German tanks use manual traverse, requiring the gunner to physically crank a wheel to rotate heavy turrets. Exhausting work, especially for the Tiger's massive turret. Crew ergonomics. The Sherman's crew stations were designed with human factors in mind. Controls positioned for easy reach. Vision devices well placed for crew positions. Adequate space for crew to operate efficiently. Emergency egress routes accessible. From the Kummersdorf report. Crew ergonomics well considered, controls are positioned logically. Vision devices are adequate for all crew positions. The vehicle is designed for ordinary soldiers to operate effectively with reasonable training. This contrasts with our approach of designing for maximum performance and expecting crews to adapt to the vehicle's requirements. The philosophy difference. German approach. Design the best possible tank. Train crews to master it. American approach. Design a tank that ordinary crews can operate effectively. Neither approach is objectively superior, but they reflect different assumptions about training pipelines, crew quality, and replacement rates. The fourth shock, reliability engineering. As engineers tested War Daddy 2's mechanical systems, they discovered reliability was designed in from the start. The Continental ER 975 radial engine. The Sherman's engine was derived from an aircraft radial engine, a proven, reliable design. It wasn't the most powerful engine for the tank's weight, but it was highly reliable, well understood by mechanics used in civilian and military aircraft, easy to maintain, parts widely available. From the Kummersdorf report, the engine is derived from aircraft practice and represents proven conservative design. It is not optimized for tank installation, but provides reliable power with good maintainability. After extended testing, we found no significant mechanical failures. The engine operates reliably under conditions that stress our own engines. Bus construction. Throughout the Sherman, engineers found design choices favoring reliability over maximum performance. Components built with safety margins. Simple mechanical solutions over complex ones. Proven technologies over cutting-edge innovations. Redundancy in critical systems. The wear testing. German engineers ran War Daddy 2 under test conditions to assess durability. They found suspension components showed wear consistent with heavy use but remained functional. Engine maintained performance despite evidence of extended operation. Transmission operated reliably despite being designed for easier operation rather than maximum efficiency. Track system, while not as durable as German designs, was adequate and easily repaired. From the Kummersdorf report. The vehicle appears to have operated for an extended period before capture. Despite this, all systems remain functional. This suggests robust design and good reliability. Our own vehicles, while superior in performance when new, often experience increased maintenance requirements as they accumulate operating hours. The fifth shock, production design features. As the analysis progressed, engineers recognized design features that made no sense from a pure performance perspective, but were brilliant from a production perspective. Welded construction. The Sherman used welded armor plate construction rather than the cast turrets and complex shapes of some German designs. Welding was faster than casting for some components, easier to repair when damaged, more suitable for mass production, achievable by moderately skilled workers, standardized fasteners, and the Sherman used standardized bolts, nuts, and fasteners throughout. American/British thread standards, consistent head types, common sizes. German tanks sometimes used multiple fastener standards within the same vehicle, requiring mechanics to carry various tools. Modular subassemblies. Major components were designed as modules that could be assembled separately and installed as units. Engine and transmission as a power pack. Weapon systems as integrated units. Suspension components as standardized bogies. From the Kummersdorf report that the vehicle is designed for mass production. Components are standardized. Construction methods are simplified. The design accepts some performance limitations in exchange for producibility. This represents a fundamentally different design philosophy. The vehicle is optimized for industrial production rather than maximum battlefield performance. The production implications. These design features enabled multiple factories producing identical components, unskilled or semi-skilled workers assembling complex systems, rapid production scaling, quality control through process standardization. German tanks designed for maximum performance required skilled craftsmen for assembly, hand fitting of components, complex production processes, limited production scaling. The sixth shock, the numbers. As the analysis continued, German intelligence provided production data that fundamentally recontextualized everything the engineers had found. The production numbers, 1943. By the time War Daddy 2 was captured in February 1943, American factories had produced over 10,000 M4 Shermans. Production rate was approximately 1,000 plus per month across multiple factories. Multiple variants were being produced simultaneously. Production was still accelerating. German tank production for comparison. Approximately 1,500 Panzer IVs produced in 1943. Panther production just beginning, limited numbers in 1943. Tiger I production severely limited by manufacturing complexity. From the Kummersdorf report conclusion. American tank production represents industrial capability of unprecedented scale. They are producing adequate tanks in overwhelming numbers. Our tanks are superior in direct combat. However, American ability to replace losses faster than we can inflict them represents strategic challenge we must address. The Sherman is designed as an industrial product for mass warfare. This is a different design philosophy than our own, and the strategic implications are significant. The ammunition discovery. A separate section of the report dealt with Sherman ammunition and fire control systems. The gyroscopic stabilizer. Engineers were particularly interested in the Sherman's gun stabilizer, a gyroscopic system that kept the gun relatively stable while the tank moved. From the Kummersdorf report, the main armament incorporates gyroscopic stabilizer for vertical plane. This does not permit accurate fire while moving at speed, but significantly reduces time required to engage after stopping. This represents sophisticated fire control system we have not implemented. The tactical advantage in close-range engagements is significant. The powered traverse. The powered turret traverse system impressed German engineers. The turret traverse is powered electric motor, allowing rapid target engagement. Gunner can rotate turret smoothly and quickly without physical exertion. Our manual traverse systems require significant physical effort, especially for heavy turrets. This creates gunner fatigue and slower target engagement. The ammunition stowage. Early Shermans had ammunition stowed in sponsons, problematic because hits often detonated ammunition, but the systematic approach to ammunition organization impressed engineers. Ammunition stowage is well organized and accessible. Ready racks are positioned for easy access by loader. This facilitates high rate of fire. However, placement makes vehicle vulnerable to ammunition fires when penetrated. This appears to be design trade-off, accepting vulnerability for crew efficiency. The armor analysis, sloping and effectiveness. Engineers carefully analyzed the Sherman's armor design and discovered it was more sophisticated than it appeared. The sloping principle. The Sherman's frontal armor was sloped at significant angles. Upper front plate, 56 millimeters at 47 degrees from vertical. Lower front plate, 51 millimeters at 56 degrees from vertical. Turret, cast construction with rounded surfaces. From the Kummersdorf report. The armor is thinner than our heavy tanks but effectively angled. The sloping increases effective thickness significantly. Our calculations indicate the upper front plate, while only 56 millimeters thick, provides protection equivalent to 75 to 80 millimeters vertical plate against our standard anti-tank rounds at typical combat ranges. This is sophisticated application of sloping principles. The design achieves adequate protection with lighter armor through geometric arrangement. The weight trade-off. The analysis noted the Sherman's armor design reflected weight management. Adequate protection for the intended role. Weight kept low enough for reliable Christie suspension. Transportation and strategic mobility prioritized. Design accepted vulnerability to heavy German anti-tank guns in exchange for other advantages. The verdict, what German engineers concluded. The final Kummersdorf report reached conclusions that contradicted initial assumptions. From the report's conclusion, the M4 Sherman represents fundamentally different approach to armored vehicle design. Technical assessment. Individual components are adequate rather than excellent. Overall design prioritizes reliability and maintainability over maximum performance. Manufacturing design features enable mass production at unprecedented scale. Crew ergonomics and training requirements are well considered. The vehicle is designed for industrial warfare and sustained operations. Strategic assessment. American industrial capability far exceeds our previous estimates. Their ability to produce adequate vehicles in overwhelming numbers represents strategic challenge. Our approach of building superior individual tanks may be insufficient against enemy who can replace losses faster than we can inflict them. The Sherman is optimized for the kind of war America intends to fight. Industrial, attrition-based, logistically sustained, tactical assessment. In direct combat, our tanks maintain superiority in firepower and armor protection. However, American tanks' reliability, maintainability, and availability advantages are significant. Their fire control systems, stabilizer, power traverse, provide advantages in dynamic engagements. Crew training requirements are lower, facilitating rapid expansion of armored forces. Recommendations. German tank design should incorporate lessons regarding maintainability and reliability. Production should be rationalized and simplified where possible. We must develop tactics that exploit our qualitative advantages while minimizing exposure to American quantitative advantages. Strategic planning must account for American replacement rates exceeding our destruction rates. The historical impact, what happened to the findings? The Kummersdorf report was circulated among German military leadership. Its impact was mixed. Those who understood, some German officers and ministers recognized the implications. Albert Speer, armaments minister, understood that American industrial capacity was overwhelming German production. He pushed for rationalization and simplification of German production. Some panzer commanders recognized that German tactical doctrine needed to adapt to numerical inferiority, avoid attritional tank battles, use superior quality asymmetrically. Technical officers incorporated some lessons about reliability and maintainability into German tank development. Those who rejected it. Hitler continued demanding ever heavier tanks with ever thicker armor and bigger guns, the exact opposite of the industrial rationalization needed. Many officers clung to the belief that German technical superiority would prevail. They emphasized the Sherman's combat inferiority and ignored the strategic implications. Design bureaus continued developing complex, sophisticated tanks that were difficult to produce in quantity. The outcome? German tank production never achieved the rationalization needed to compete with Allied numbers. Tigers and Panthers were magnificent machines when they worked, but there were never enough, and mechanical reliability remained problematic. Meanwhile, American Sherman production continued at scale. By war's end, over 49,000 more Shermans produced. Continuous production from 1942 to 1945, supplied to US, British, Soviet, and other Allied forces. Formed backbone of Allied armored forces. The ratio. For every Tiger I produced, 1,347 total. The Allies produced approximately 36 Shermans. For every Panther produced, 6,000 total. The Allies produced approximately 8 Shermans. The numbers told the story the Kummersdorf report predicted. The legacy. What war Daddy 2 taught. The captured Sherman's analysis revealed truths about industrial warfare that remain relevant. Lesson 1, adequacy at scale beats excellence in scarcity. The Sherman was adequate for most tactical situations. German tanks were excellent in direct combat, but adequacy produced in overwhelming numbers defeated excellence available in limited quantities. Lesson 2, sustainability matters as much as capability. A tank that breaks down frequently or requires extensive maintenance is unavailable for combat regardless of its specifications. The Sherman's emphasis on reliability and maintainability created availability advantages that mattered strategically. Lesson 3, industrial design is strategic design. The Sherman's producibility features, interchangeable parts, simplified construction, standardized components, enabled the industrial output that won the war. These weren't compromises, they were strategic features. Lesson 4, logistics shapes tactics. The Sherman's maintainability meant more tanks available for combat. The resupply advantages of standardized parts meant better sustained operations. These logistical advantages created tactical opportunities. Lesson 5, different wars require different tools. German tanks were designed for short, decisive campaigns, blitzkrieg. American tanks were designed for sustained, industrial-scale warfare. Each was optimized for different strategic contexts. The fate of war, Daddy 2. What happened to the actual captured Sherman? Known history. War Daddy 2 remained at Kummersdorf for extended testing through mid-1943. It was used for Ammunition effectiveness testing, German guns versus Sherman armor. Mobility testing in various conditions. Crew training, teaching German tankers Sherman characteristics. Comparative testing against German tanks. Likely fate. Records suggest the tank was eventually damaged during testing, deliberately shot to test armor, possibly destroyed during Allied bombing of German facilities, may have been captured by Soviet forces overrunning Germany in 1945. No confirmed surviving examples in museums. The symbolic importance. War Daddy 2's physical fate matters less than what its analysis revealed. That captured tank, stripped apart at Kummersdorf, told German engineers that they were fighting a different kind of war than they'd prepared for. They were fighting for battlefield excellence. America was fighting with industrial might. The engineers who analyzed War Daddy 2 understood. They wrote clear warnings about what American industrial capacity meant. Those warnings were largely ignored by leadership that couldn't abandon the belief in German technical superiority, even when the evidence was literally bolted, welded, and riveted in front of them. Conclusion: the tank that revealed the war. February 1943. A Sherman tank was captured at Sidi Bouzid during one of America's worst early defeats in North Africa. German engineers expected routine analysis confirming American technical inferiority. Instead, they discovered a tank designed for a different kind of war, a tank optimized for mass production, field maintenance, crew sustainability, and industrial-scale warfare. Every feature they initially dismissed as crude or unsophisticated turned out to be deliberate design for industrial warfare. Interchangeable parts enabling rapid field repair and multi-factory production. Simplified controls enabling faster crew training and sustainable operations. Reliable components prioritizing operational availability over maximum performance. Production-friendly design enabling unprecedented manufacturing scale. Maintainability features allowing battalion-level mechanics to keep tanks operational. German engineers wrote clear assessments. American industrial capacity exceeded German estimates. The Sherman was designed for mass warfare. German qualitative advantages would be overwhelmed by American quantitative advantages. They were right. Their warnings were ignored. By war's end, 49,000 plus Shermans produced versus 7,500 German heavy tanks, Tigers and Panthers. Allied armor available in overwhelming numbers. German tank units increasingly immobilized by fuel shortages and mechanical failures. Industrial warfare decided by production capacity, not individual vehicle excellence. The captured Sherman that arrived at Kummersdorf was more than a tank. It was a message from American industry. We can build adequate tanks faster than you can destroy them. German engineers understood the message. They documented it carefully in technical reports that still exist in archives today. The leadership that could have acted on those warnings chose to believe German engineering excellence would overcome American industrial might. War Daddy 2, a single captured tank torn apart by German engineers seeking to confirm their superiority, instead revealed the truth about industrial warfare that would determine the war's outcome. The tank was inferior on paper. The industrial system that produced it was unstoppable in reality. That's what German engineers found when they looked inside War Daddy 2. Not crude American manufacturing, not unsophisticated design, but a machine built by a nation that understood this war would be won in factories, not just on battlefields. They were looking at defeat, manufactured in Detroit, shipped to North Africa, and now sitting in pieces on a German testing ground, revealing exactly why Germany couldn't win an industrial war against American production. The tank spoke clearly. Few listened. Those who did understood, the war was already decided. The only question was how long it would take American factories to produce enough adequacy to overwhelm German excellence. War Daddy 2 answered that question for anyone willing to read the engineering reports